All right, good evening, everybody, and welcome back to another live stream. Today's going to be a fun one for me. It's kind of a big milestone, if you will. So I've mentioned in previous streams that I would like to do like a series where we eventually build our own large language model. And so that's going to be a long series. And to be completely honest, I have shiny object syndrome. So it's not going to be as if this is like the first stream and then the next few streams are going to be this building of an LLM. There's probably going to be other content interspersed throughout. I've definitely not forgotten about like the LLM evaluation that we began with. So like we did the MMLU a couple weeks ago. I've set that aside. I keep jumping from topic to topic, but so yeah, tonight we are going to cover tokenization. Now, before we jump into tokenization, I do kind of want to address a little bit of the elephant in the room. And maybe many of you are probably not even aware of this. So AI expert engineer Andre Karpathy. So he, former head of Tesla AI, one of the founding members at OpenAI, and then went back to OpenAI for a short time. Now he's gone again. He recently he produces his own YouTube videos that are absolutely excellent. I would absolutely recommend you check them out them all. He's not necessarily done one on tokenization before, but he happened to do one on tokenization just this week. So this looks oddly sus of me, if I can use that term, if you will, where it seems like I might be copying his work, but I promise you, that it's purely coincidence that I started my work at the exact same time that he did. Now to be completely transparent with you, his tutorial is so well done that tonight's is largely going to be founded on what he did. So I very much encourage you to go ahead and check out his video after the stream. There is going to be a bit of overlap. However, there's going to be a lot of content that we're not going to cover that he covers over in his stream. And then also things that he touches on that he's going to better explain than I probably can. So, yeah. Losing my train of thought a little bit there. All right, so another bit of transparency here. Last week I was in Chicago and I did an executive public speaking course, which is really good. It was really exciting. Learned a lot about myself. It was one of those things where they filmed us a bunch and we would give feedback on each other. It was a great group to work with on things that we could be doing better. So that's one thing that I'm going to be practicing throughout this stream here. And my biggest problem that I've noticed is this run-on sentence stream of consciousness kind of thing where I don't stop to breathe. So if you noticed that I'm pausing more or I'm taking like more breaths or whatever, that's why. But we're still gonna have a lot of fun in this stream regardless. Okay, so lost my train of thought there again. All right, let me pause, breathe. All right. So what we're going to be talking about today is, like I said, tokenization. I do want to take a step back to understand why tokenization is important. So when you think about in the context of large language models are essentially next word predictors. Now, of course, there's other variants of large language models, but the ones that you're familiar with, like ChatGPT, they're very much next word predictors. And as we go into the process of building our own large language model, LLM, what we are going to need to do is we're going to need to find the relationships between words, if you will, and not necessarily words, but I mean, we're jumping ahead a little bit, but down between tokens. But let's stay at the level of words for now, because there are two like streams of thought, if you will, here. So let me actually go ahead and jump into my screen here, because it's going to be easier to kind of illustrate this with a little bit of an example before we actually start getting into the code. Okay, so imagine here. Let me make this bigger for y'all. Okay, and by the way, I am monitoring for questions on YouTube or LinkedIn. I still don't know how to check questions. Excuse me. I still don't know how to check questions over on X, so I apologize for that. Okay. Where do I want to begin here? Okay, so let's talk about three words here. Did I make that bigger already? I don't know if I did or not. Okay, that's big enough. That's like geriatric size for me. All right, so consider these three words. Drop. Well, I'm going to make this into a markdown cell. Sorry about that. All right, so drop, dropping, dropped. Okay, so these are just three standard English words that we're all familiar with. So right now, I would say these are conjugated in their verb form. So if I drop, if I drop my water bottle here, it's going to hit the ground. If I'm dropping my water bottle, I'm in the process of dropping it. Or if I've dropped the water bottle, then the past tense, the water bottle's already been dropped. So the temptation here is why don't we just go throughout the entire English language and start tokenizing based off of all of these words? There's a problem with, so that's an understandable thought, but there's a problem with that sort of thinking. And that is, we start treating these as individual tokens then and start looking for the relationships as if these are different words. And that's not ideal. What we would prefer instead to do is sort of treat all of these words the same. And then even such, so we're talking about in the the verb form, but drop can also manifest as a noun. So like a water drop, like a raindrop, something like that. And so it's and the other thing too is if you try to encode every single English word as this, then your vocabulary and your tokenizer just becomes extremely big. And also to mention, like when we do our tokenization, we also tokenize things like punctuation or emojis or other languages. So like if you are a Korean speaker or a Chinese speaker, you use special characters that are not unique to like the English language. So this is not an ideal way to trying to measure the relationships between tokens in a large language model context. What's more, so let's go to the other extreme. Let's chunk all these down. Like let's say I wanted to take the word drop, and then let's turn every single character into its own token as such. So drop would then become DROP, and then each of those would be saved as their own tokens. Now, this is actually, conceptually speaking, not a bad idea. The unfortunate part with this is that whenever it comes to like the training of the actual LLM itself, this just becomes way too computationally expensive. This is not feasible to maintain in the long term. Like maybe in the future, so this is one thing that Karpathy talked about in his video is like there are people looking to see if we can just do full we'll talk about this in a little bit, but byte streams, if you will, into here. So there's research going into that, but that's also not a great path. So we've got the two ends of the spectrum now. We've got let's tokenize on all of the words here. And we've discovered and we talked about why that's not a good idea. And then the other end of the spectrum, we've got the individual little byte pair, like the little bytes here, the characters, if you will. And can we just use those instead? And computationally speaking, unfortunately, that's not going to be feasible. So what is this happy medium, if you will? All right, so there is more than one way to tokenize things, but the one that we're going to focus on tonight, and the one that and again, I promise I looked this up before Karpathy's video came out, is we're going to be looking into what is called byte pair encoding. So let's jump on over into the Wikipedia page that talks about byte pair encoding, and again, full transparency, Andre does this exact same example as well. It's just a really simple example, and it's the one that we're going to use to illustrate everything that we're going to be doing in code tonight. Fortunately speaking, this is actually a really simple sort of concept to understand. So imagine that we have this bit of text here that we want to encode. Now, this is a bunch of random characters here. Now, what we basically want to do with byte pair encoding is we want to replace any of these tokens that kind of show up together as pairs into a new token, and it doesn't really matter what that token is. So let's step back and let's talk about why it doesn't matter what that token is necessarily. So I'm going to illustrate with this video game. It's a rather new indie video game called Chance of Sinar. It's pretty fun. Basically what happens in this video game is you are this character that is dropped into this world where you do not know the language or anything, and you kind of just are got to figure your own way around the language, so or around the land here. But there's a lot of context clues given throughout the land here. So you can see eventually, like, all right, so here's some arbitrary characters. This is one of the first things that you come up in the game. This is a very minor spoiler if you ever want to play the game, but trust me, it gets harder from here. So you can imagine, or so like using the context character clues here. So this lever is next, you can't see it here, but it's next to a door. And so you can see off on the right here that if you pull the lever up, then like we have these glyphs here. Or if it's down, then you have these glyphs here. And so using the context clues, you could say, okay, well, I know that the word, we're working with a door. So it kind of makes sense that maybe this left parentheses and this upside down T represents the word door. And then because it shows up twice here. And then maybe this like this other glyph here with like this C-like line and the line underneath it, maybe that means open. And then this one down here means closed. And so that's how the basic premise of the game works, is that you can use context clues to kind of figure out what things mean, even if the glyph is totally arbitrary. And so that this analogy plays very well along to what we want to talk about with tokenization tonight, is as we go through this byte pair encoding here, is so you can see that, you know, with this Wikipedia example, they gave very specific encodings. So like in, you know, this isn't necessarily how we're going to do it at the end with byte pair encoding, but we'll work with this example anyway. You can see here that they replaced the token AA with the letter Z. And so again, if we were to pass, and after it does all this merging and stuff, so after 3 merges of like this byte pair encoding, we end up with this output here. Again, if this is a little bit confusing right now, this will make perfect sense after we start to jump into the code here. So this is what our end state of the encoding value is going to be. So imagine this is going to be what is eventually passed into the large language model. Again, it does not matter that we are using arbitrary characters here to represent different underlying concepts. And it goes back to this thing like I talked about with Chance of Sonar here, is like as long as the sequencing of these things remain the same, that's good. We could take the word pizza and we could encode it into ASDF GHJKL, which, I mean, that would be really silly. But like as long as we're keeping the sequencing of the words the same, it does not really matter. So I just want to give a little bit of a primer there, because like you might be wondering, like because we're going to be minting, if you will, new tokens, and these tokens are going to be arbitrary. Now, like I said, so in this Wikipedia example, they are giving very specific values, but in most in like an actual tokenization context, the tokenization is just going to be like, imagine if this is a separate letter A and a separate letter A, the new token is just going to be the merged version of these. So it's actually pretty intuitive. It's just that like this, I think this Wikipedia article is just really trying to drive home like you know, what this example looks like. So all right, let's go ahead and iterate through this manually. So let's go ahead and take our sample, and all right, so I'm going to come back into here. Hold on just a second. All right, so all right. Okay, so this is going to be our input text that we're going to be working with, or our sample text. We'll call it our sample text. All right, and then expected output is going to be whatever was in that Wikipedia article. So the expected output after the merges is going to be this. Okay, or this. Okay, now I keep using the word merges. So basically, what is going on here is when we want to do this byte pair encoding, we set how many times we want to run, how many times we want to try merging these tokens. And we'll talk about that more in a little bit. But let's go ahead and try to do this just sort of manually. So like I said, you know, Wikipedia is assigning some arbitrary tokens. So let's go ahead and set what those arbitrary tokens are, just to keep ourselves sane. So basically, they're going to say AA. It's going to turn into the letter Z. AB is going to turn into the letter Y, and then zy, notice it's going to be a merging of these two new tokens, is going to turn into the letter X. Okay, so, and this is going to be after 3 times that we run this sort of algorithm. So let's go ahead, like, again, if this is not making sense, let's go ahead and do this by hand. So iteration 1, so what's our input look like? Our input text, here, I got to move some stuff down. Okay, our input text. Well, you know what? This stream's gonna get really long if I just don't copy and paste this in. So let's just go ahead and copy and paste this in. And here, let me go ahead and grab it from my other notebook here. By the way, I do have obviously I have a much cleaner notebook up on GitHub. So this is gonna be our messy working copy notebook. So don't worry about this too much. But I'm just gonna copy this in here. That is not what I meant to copy. I meant to copy this. Okay. Oops. Okay. All right. So first pass. Iterations. I'm going to call this iterations. All right. So in a first pass, this is our raw text. So what we first want to do is we want to iterate over, like have a sliding window of over all this text that is basically looking at the byte pairs and then basically doing a count to find out which is the one that it appears the most frequent. So you can imagine if we have a sliding window here, the first one's going to be AA. The second one is going to be AA again because that's what the byte pairs are there. Then the next one after that is going to be AB, then BD, DA, AA, et cetera, et cetera, et cetera. And so just by eyeballing it, you can kind of see what the most frequent byte pair is, and that is going to be the letter AA. Now, like I said, we want to replace the AA with this arbitrary token of Z, as I mentioned. So if after we've determined that, so what we want to do then is we want to go back through, and let me just, I am going to go ahead and just manually do this just to really drive it home. So like, let's say, so this is our original input text. We want to go back through every time we see an AA like this in this order, we want to replace it with the letter Z. So there's that. And then we got this one over here. Let's go ahead and replace that. All right. And so you can see here now that is the end of the first iteration. And that right there, folks, this iteration 1 here, that is basically the byte pair input coding algorithm. Good night. So see you later. So it's, like I said, it's a very simple concept. I'm just joking. We're not actually going anywhere. It's a very simple concept. It's just that we need to keep doing this over and over and over until we build up a vocabulary that we're happy with. So let's go ahead and go through the next 2 iterations. So again, we're starting off with our iteration 2 here. So let's go ahead and kind of just eyeball it here to see like where we think the most frequent byte pairs are. So in this case, it is now going to be AB, AB, AB. And I think that's right. I feel like I may have messed something up in here in my example text here. AB, ZA, ZA. Because I'm kind of wondering why it's not ZA now. I don't know. I'm just going to keep going with our sample text here. So like basically, so we find that the most common pair here is AB, and we want to replace all the ABs with Ys. So now we come back in here. So same concept again here. Let's take this, bring it on down. And then, like I said, anywhere where we see an AB, we're going to replace that with a Y. So again, any place we're going to see it, where we see an AB, replace it with a Y. And then finally on our third iteration, let's eyeball it again. What's the most frequent pair here? Well, the most frequent pair here, as the spoiler alert shows here, is ZY. And so we like we should note up here, we want to replace the ZY with the arbitrary text of X. Now, one important thing to note here is the order in which we merge things absolutely matters after the fact. So right now we're just training the tokenizer, if you will, on an arbitrary set of text. Now, obviously, we're going to pass in new text that the tokenizer has not seen before. And so when we encode that new text for tokenization purposes, we need to basically follow the same path of like how the merges work here. And I hope that this example really illustrates why. And the reason is you can see that in our first pass, the most frequent pair was like within the raw text here. But as we got further down the line, specifically onto iteration 3, you'll notice that the most frequent pair was actually a combination of two newly minted tokens that did not show up before. And so obviously that's going to wreck things if you try to like jump toward the end and try to just tokenize everything at once. No, you need to really follow the iteration order of these things. So again, so that is really the byte pair encoding algorithm as a whole. Now, this is a bit of a naive take. We'll talk a little bit more about why this is naive in the end. But let's go ahead and code this thing, because there's a lot of code here. It's relatively straightforward code, I hope. But yeah, let's go ahead and jump into things. So I'm going to set my sample text here. Again, text to equal. Did I already set it up here? Yeah. Well, I'd set it up in Markdown, but not in Python. So let's go ahead and bring it on down. All right. Sample text. Oh my gosh, if I can type right. All right, sample text there is instantiated. Okay, so one of the very first things that we want to do is to instantiate our vocabulary. So what we're going to be doing here is we're actually going to be using byte values that are representative by in UTF-8. So UTF-8 is this Unicode. What does UTF-8 stand for? Or what UTF? All right, hold on. UTF. Hello. Unicode transformation format. And basically, so this is probably a good image here. Yeah, this is not a bad image. All right, so basically what this is doing is, so your computer I'm not going to go too deep into how a computer works, but basically, a computer is running on binary ones and zeros, so it likes to work with bytes and whatnot. And so as new characters are added to like a corpus, so like, imagine, we're going to be working with English characters, but there's also, like I said, Korean characters, Japanese characters, Chinese characters, or emoji, things like that. We want to have a clearly defined way to to know how to encode these things in byte form. And so that's what this whole UTF-8 sort of thing is here, is it's going to be transforming our text, our raw text, into something that we can work with in a numerical fashion in a sort of consistent sort of manner. Like, so let's go ahead and illustrate with a little bit of an example. All right, so like imagine that I got my I'm gonna this text here, my name equals David Hunley. All right. So nothing special about my name here. It's just standard English characters. So let's go ahead and encode this to see what it looks like. So I'm gonna say print, or I'm just gonna say list my name. So it's just a string. So on strings in Python, we can just call this function called encode, and then we're gonna set it as UTF-8. And let's just go ahead and run this and see what it produces. Okay, so as you can see here, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 12 characters in my name plus the space in between there. So the space is represented by the number 232. So again here, so this is how this kind of works. So that's how it works for like English characters. Now imagine like I popped in an emoji here. So let's say emoji equals and it doesn't matter, we'll just pick one at random. The panda. How about the panda? All right, so now let's go ahead and do this again. So list emoji dot encode UTF-8. Okay, so now you can see here for this one single character, we have 4 different byte values that represent the one character. So again, this is why this is sort of a preferable path here, is that this UTF-8 is going to be consistent over time. And so if we add new characters over time, like let's say, the Unicode consortium is always adding new emojis. And speaking of that, soapbox time. I really want a database emoji. Just give me a database emoji. Like, we have emojis for everything. I want the little canister looking icon. Please, Unicode Consortium, add that to here. So you can see, all right, so, but like, we're not going to be working with emojis tonight. Again, we're just going to be sticking with our plain text, but I just wanted to highlight this here. This is why we end up doing these things. So the first thing that we want to do before, I'm jumping ahead a little bit. So so we want to have a vocabulary that we can continue adding these newly minted tokens to. Now, if you're not familiar with bytes, bytes do range up to 256 bytes. So we're going to instantiate our vocabulary with that. So I'm going to call this vocab, and this is going to be a dictionary. Let me look at my notes here. Notes. Not doing a good job with my breathing. I can tell that. If you're just now joining, I mentioned early on in the stream that I took an executive public speaking course last week, and I learned that I need to pause more frequently to gather my thoughts and not have this like crazy running train of thoughts all the time. So yeah, I'm working on that tonight in this stream, and it's not going well. It's hard to think and talk and type all at the same time too, which is why I do most of this like pre-work beforehand. Okay, so where is that vocab? Like, I'm looking at the notes here. Okay, so this is going to be an index. So what we want to do is it's going to be, we're going to have the index value, and it's going to be the bytes version of the index value for IDX in range, like I said, 256. All right, so let's go ahead and look at what that is. All right, so you can see here, we have this dictionary of values here. So earlier on, we have so here's like at the 0th place, we have like just some bytes values. And then as we go on further, we start to see some of the more standard values that we are typically familiar with. So I mentioned earlier, like the space between my name is the value of 32. So if we come down to 32 here, you can see just that. And again, so Andre in his video, he does a much better job at explaining the value of UTF and some of the pitfalls of UTF, and we'll talk about the one of those pitfalls a little later on. Again, check out his video. He's obviously the expert here. I'm kind of just learning things as I go here, and learning in public, if you will. Okay, so that's our vocab, and so what we're going to be doing is, as we keep doing the iterations of this byte pair encoding algorithm, we're just going to start adding new entries to this dictionary, and we're going to start adding them at the end. Like I said, there are 256 bytes, but of course indexing starts at 0. So our first real byte is actually going to be at number 256. Now, one thing I do want to call out here really quick is in this Wikipedia example that we're working through, we are using very specific arbitrary tokens. Again, this is just an example to really kind of highlight it here for Wikipedia's purposes, but in real life, the newly minted token is going to be the combination of the separate tokens. So what we need to do here, just to make this example work, is we need to create just like a little sample lookup just to handle these arbitrary tokens. So I'm going to call this a Wikipedia example lookup. And like I said, so the first pass, which is going to be the first, like this 256 entry, is going to be the bytes, is going to be the Z token, and then in the second pass, which is going to be at that value, is going to be the Y token, and then at the third iteration is going to be the X token. Okay, so this will come back, like, again, this is not going to be relevant in a real context. This is just something to make our example work. And unfortunately, like, that's all we need to do to make this sample work. Like, that, there's nothing really else fancy that we need to do. And again, it'll make sense here in a little bit why we did that. Okay, so all right, let me look at my notes here. All right, so as I mentioned, now that we have our sample, here, let me go ahead and just print it out again. We have our sample text. What we want to do here is now we want to, so back to back to our example that we went through at the top here, is basically over each iteration, we want to find the most frequent pair, mint the new token, update what the input text looks like, and then I don't have a fourth step on here, but we want to do two things. We want to capture how these things were merged. And again, it goes back to that whole thing is when we want to tokenize new text, we want to be able to follow the same merge order, because if we don't follow the same merge order, then things get a little bit wonky. And then we also want to update our vocab that we just created. Okay, so the very first thing that we need to do is we want to find the most frequent byte pair in the string here. All right, so what we are going to do here for this is I'm going to, so this is a default Python library. We're going to import from collections, import dec here. So that's pronounced dec. So if you're not familiar what this is, this dec stands for on cue DQ, and like basically what you can do here is you can set like this dec here to have like a fixed length. So let's say you have a fixed length of 4. And so what that's going to do is every time you add something to this dec, it's going to keep adding until it's hit 4. And then if you try to add something else, then it's going to like shove the first item out. So as you can imagine, this works really well for sliding windows, is we just keep adding so in this case, we're looking for just the pairs. So our dec is only going to be 2 items long. So as we add each new individual letter from this text here, we are just going to push out the previous one before. So it works very well for sliding windows. So I'm going to call we're going to call this function get BP freaks, get BP and then freaks. So that's just short for get byte pair frequencies, and we're going to pass in our token IDs. So I guess I didn't did not encode our sample text quite yet. So we're going to call, like I mentioned, so we just want to generate our token IDs in byte form. So what we need to do here is we need to get a list of our sample text, .encode with UTF-8. And then just to show you what it looks like, let's just go ahead and print that out. All right, so token IDs. All right, so here's our raw token values based off of the byte form. And again, so what we're going to be doing here is when we pass this into this get byte pair frequencies sort of function here, is we're going to build like a dictionary of which one of these kind of shows up the most often. And again, that's where this dec comes in handy here, because we can do this sliding window sort of thing to make this pretty easy on ourselves. All right. So like I said, this is going to be a dictionary. So we're going to instantiate a dictionary called BP freaks. So this is going to save all of our byte pair frequencies and note how many of them show up over time. Now I'm going to, like I said, we're going to use this dec here to perform the the sliding window sort of functionality. So BP window equals dec, and so we're going to set a max length on this dec to 2, because we only want to analyze 2 of these pairs at a time. And now let's just go ahead and start going over each of these byte pairs. And so I'm going to call it, so right now they're just in a like raw sort of state here. Now you can imagine over time, like as these get merged, they're not going to be in a raw sort of state. So that's where I'm trying to avoid using the word bytes where I don't need to. So I'm going to call this just byte pair. So for BP in token IDs. So for BP token IDs, so first thing we want to do is we want to append our byte pair to the sliding window here. So BP window dot append BP, and then so now obviously we only want to start tallying them up after we've had 2 pairs. So in this the very first one, obviously we've only got 1 inside, like we'll only have 1 value inside of this dec. So we don't want to start doing the new byte pair analysis until we've at least have 2. So basically what we want to do is, if length of the byte pair window is equal to 2, or I guess you could even say not equal to, no, I'm going to say equal to 2, then we start doing our thing. So so the new byte pair, so we're going to extract the new byte pair. and we're going to extract it as a tuple. We want to, and so if you're not familiar with what a tuple is, it's a immutable sort of thing that you can just add values to and reference them. It's sort of like a list, but it's immutable. So we're gonna set this as a tuple. All right, and so the BP window. Okay, and then we want to. So we got our dictionary up here. We just want to start adding stuff to it. So BP freaks. All right, so our new byte pair, so that's going to be the key, is going to be BP freaks dot get. So we're either going to just increment the byte pair if it's already been in there. So like with AA, like after like the first or second pass, we're just going to increment the value of that dictionary. But if it's not there, we're going to instantiate it to 0. So that's why we're using this get function here on the dictionary. So BP new byte pair or 0, and then we're going to increment it by 1. All right, and then after this runs, we're just going to return the BP frequencies. Okay. All right, so let's go ahead and run this on our input text or our token IDs that we've extracted from our input text, just to show you what it kind of looks like. So I'm going to call this BP freaks equals get BP freaks, and then we're going to pass in our token IDs. Token IDs equals token IDs. All right, and let's go ahead and print this out. Freaks. Okay, so you can see here we have these are all the byte pair frequencies that we derived here. So you can see that 9797 shows up 4 times, 9798 shows up 2 times, and then we got, the other ones just show up 1 time. So you might be wondering, we're starting to already get a little bit of an indication here of what this 9797 is. Obviously, if the numbers are the same, that means the character is the same. So in Python, if you want to check this out, it's actually, the CHR function here. So if we pass in just an integer value, so if we pass in the number 97, guess what it's going to be? It should be obvious. It's the letter A. And so obviously, with our first pass here, coming back up to the top here, our first merge is going to be these AA. So this should not be a surprise to us here. Okay, and just for fun, if you're not aware, you can also do the same thing vice versa in Python. So if you have a character value, when you want to get the byte value associated to that, it's just using this ORD function. I don't remember what ORD stands for. So let's just pass in the letter A, and so you can see again we get the number 97 back. Okay, so those are the byte pair frequencies, and so now that we have the most, so let's go ahead and save this. What we want to do is we want to extract out what was the most the most frequent byte pair, which is this one here. So I'm going to call this here most freak pair. Excuse me. And the way that we can do that is we're going to get just the maximum value of our byte pair frequencies, and we have to set the key here. This is just a Python thing, to bp.freaks in order to get that key value, or the key appropriately from there, based off of the value associated to it. And again, let's bp.freaks. There we go. And then let's just go ahead and print that out. Okay, so as you can see, our most frequent pair is 9797. Okay, so now what we need to do is let's come back up to our example at the top here, and let me go ahead and this cell's going to drive me nuts. So I'm going to comment that out, or not comment that out, but just remove that thing. So now what we want to do here, all right, so we've determined that our most frequent pair is AA, and we want to replace the AA with this arbitrary value of Z. Now again, I can't reiterate this enough, just for clarity's purposes. In a real byte pair encoding algorithm, we're not gonna assign arbitrary values like this. We're gonna take instead what we're gonna take as the new token is the letter A plus the letter A together, and make it AA. So actually, in the real sense, so what this would become, so we've assigned AA to Z, and then AB to Y, and then ZY to X. So if we were to work the way back through here, what it would actually be is that this X token would be AA AB, because the AA representing Z, AB representing Y. And let me just type that out here really quick to make so that makes sense. So this equals AA AB. And that's in a real byte pair encoding algorithm. That's how the token is going to manifest. And again, if the no, never mind. I was going to explain something there, but I think I was going to explain it in a poor way. So let's come back down here. So we have our most frequent byte pair. So what we want to do is now we want to take our token IDs here, the same token IDs that we derived right here, and basically anytime we see a 9797 in this direct order here, we want to replace that with the newly minted token. So like I said, when we instantiated our vocabulary, we did it by the number of bytes that are the total number of bytes, which is 256. But we started indexing at 0, so our vocabulary actually ends at 255. So which means that our next token is actually going to be 256, and then we went to mint this new Z token. All right, so let's go ahead and hold on, I'm looking at my notes here. Let's go ahead and create a new function here that is going to allow us to do this merge pretty simply. So we're going to call this def merge token ID. So we're going to pass in 3 things. We're going to pass in the token IDs that we've been working with. We're going to pass in the replacement pair. So in this case, it's going to be the most frequent pair here. Now I'm calling it replacement pair here and not most frequent pair because we're going to reuse this function for something later on. Don't worry about that quite yet. What time is it? Oh my gosh, we are flying. I knew this was going to be a long stream, but I'm afraid this one's going to be a really long stream. The good news is we already covered the intuition. So like really, like as long as you understand the intuition, the rest is just how do we manifest this and make it automated and whatnot. So don't worry if you have to drop off, whether you're on LinkedIn, X, or YouTube, all of the streams are saved across all these 3 platforms. Okay, so all right, so I lost my train of thought there again. All right, so we need to pass in the merge token ID. Also, so I'm calling it merge token ID. So this is basically the newly minted token that we want to replace things with. So in our first case here, it's going to be the letter Z. All right, so we're gonna first. And so what we're going to return after this is basically a new set of these token IDs, except again, it's going to have some merge things here. So, excuse me, I thought I had to sneeze. So what we're going to do here, so this is just a list of values. We're going to create a new list here. So we're going to call this new token IDs. And we're just going to instantiate this as an empty list, and then we are going to set a cursor here. So like and basically as we index over this token IDs here is when we get to the point when we find a matching pair, is we basically want to add that back into this new token IDs and then jump forward 2 spaces, if you will. That way we are effectively encapsulating the byte pair and replacing it with this merge token ID appropriately. All right, so we want to keep iterating over this while I is less than the length of the token IDs. So basically keep going until we can't. Token ID, token IDs. Oh my gosh, need to type. All right, so the first thing, like I said, so we want to be able to check is if what we're currently analyzing, does it match this replacement pair that we're inputting here? That doesn't look like I spelled it right, but okay, I guess I did. All right, so we're gonna check the token IDs. If token IDs at the ith position equals the replacement pair, the first part of the replacement pair, and if the token IDs at the next position after this, so that would be i plus 1 is equal to the replacement pair in the second position. So that's what we're checking for. And then the other thing that we also want to check is to make sure that we are. Oh, my notes aren't. Hold on, I'm gonna have to grab it from here because for some reason my notes down below are being funky. Merge token ID. And as long as we're not at the very end here, so that's what this little bit's encoding. Like I just couldn't see it on my other screen for some weird reason. So, all right, copying it back into here. And all right. So as long if that condition is satisfied, what we're going to do is we're going to at our new token IDs, we are going to append this new merge token ID. And so again, in this first context, this is going to be, so we're replacing the letters AA, which is 9797, with the token ID value of the letter Z, which is an arbitrary value, and that's going to be, in our dictionary, that's going to be the 257th entry, which is the index of 256. I hope you're following along, because this is, when I say this stuff out loud, I kind of hear myself and I think, this doesn't make sense. I mean, it does make sense in my head. Again, I can't stop coming back to here, because the intuition's more important than anything. And I think this intuition of working through yourself through this simple Wikipedia example is far more helpful than anything that we're going to do here in the form of code. Okay. All right. So we want to merge that. And if not, then we just want to basically pass this through. So so in this case, this token 98 here, we're not replacing that. So we're just going to pass it back through and add it back to this token ID. So we're just going to say, oh, I forgot. We do need to move the cursor. So we're going to move our cursor 2 spaces. So we're not analyzing the next token. Okay. So, and then, as far as passing through the ones that we're not altering, so we're just going to do new token IDs.append token IDs at the ith position, whatever that is, and then we're going to just move the cursor 1 space ahead. I plus equals 1. And then finally, we just want to return the new token IDs. Okay, so let us go ahead and perform our first merge. All right, so I'm going to call this first merge. And then what we're going to do is, like I said, we're going to, in this merge token IDs, so token IDs equals token IDs. And then replacement pair. So like I said, this is going to be our most frequent pair. And then our the merge token ID that we're going to be adding. So this is the newly minted the ID for the token that we are currently minting. Now we're going to hard code this value here just for simplicity's sake. So this is going to be the one right after our initial vocabulary. So as you recall, the last entry on our initial vocabulary was 255. So next one is obviously going to be 256. All right, so let's go ahead and, all right, I want to, all right, what did I call this up here? All right, token IDs. I'm going to print token IDs, and then I'm going to call this print first merge. Okay, so now you can see here, so this is our original kind of stuff here. So you can see the first 9797 has been replaced with 256. And then we skip over the next one because 9798 does not match our most frequent pair that shows up. 98-100 doesn't match, so on. But then we come across again another 9797. Boom, replace that with a 256. And then 9798 we'll pass through, and then that basically completes our first merge. Okay, so now, like I said, coming back again to our original example, we want to be able to save the ordering of these merges. So when we want to tokenize new text, we want to follow the same merging pattern here. So what we need to do two things. We want to save the merge order, and then we also want to update our vocabulary effectively. So let's go ahead and first save that merge order. And so I'm going to call, and this is going to be like a lookup dictionary. So I'm going to call this merge order. Merge order is dictionary. Again, and so for folks who are just now joining, this notebook's going to get really messy, but I have pushed up a much cleaner version of the notebook to GitHub. And it's got a bunch of the different markdown text. Honestly, this is so I did this like earlier today, or I guess earlier today and over the past week. So this is basically the exact same thing that we're going through tonight. And this is actually what I'm referencing on my screen down here. So this is, if you're having a hard time following along, I hope that this other notebook makes a lot more sense, but this is live coding. So I wanted to do it live for y'all. All right. So like I said, setting the merge order. So first thing that we want to do is we want to, merge order So we want to set our most frequent pair. So again, this is going to be 9797 to equal the value 256. So that's just hard coding that there. So let's go ahead and print out the merge order. Print the merge order. Okay. So this is going to be a lookup table that we're going to keep adding things to over time. So for this simple Wikipedia example, since we're only running this byte pair encoding algorithm 3 different times, there's only going to be 3 different entries here once this is all done. So right now we're just taking it baby steps at a time. We're just doing the one merge for now. We're just going to keep working through this. We will bring this all back together, so don't worry about that, and we'll clean up the syntax and whatnot too. All right, so we updated the merges there. Now let's go ahead and update our vocabulary. So vocab at the 256th position. So this is where our little lookup table is going to come in handy. So this is where we said basically we want to assign this very arbitrary token here, just so we can continue following along with our Wikipedia example. Okay, so all right, vocab 256 equals Wikipedia lookup, and then we're going to pass in that 256. And then let's go ahead and look at the last few entries in this dictionary here. So I'm just going to paste this in. Don't worry about what this is doing. This is just a simple shorthand to be able to look at the last few entries here. All right, so these are the last few entries. So you can see 252 through 255 are just standard like byte encodings that we got from UTF-8. But now we have at the 256th position, we have our new token, and that is the byte encoding value of this arbitrary Z character. All right, so that is, I mean that really consists of like the basic ordering of how we want to do this. So now we basically just need to keep running this over and over. So now, like I said that we want to jump, we don't want to jump too far ahead, but I guess here we are. Like we're just gonna go ahead and run the 3 merges here. So some of this code is gonna be a little bit of the samey, but let's talk it through as I type this out. So vocab equals so IDX. All right, so this is just the instantiation of the vocab here. We are reinstantiating it from scratch, just for clarity's sake. So in range 256, and again, the reason it's 256 is because there are 256 bytes that we can work with. Okay, so and then again, we want to instantiate our merge order dictionary. Merge order equals that. And then we are going to get our token IDs. So this is going to be the list, like basically taking our sample text, encoding it with UTF-8, and then expanding it into a Python list that we can work with. UTF-8. 8. Oh my gosh, if I can type. All right, and now we're just going to go through each of the 3 different iterations here to produce the final output for this Wikipedia example. So I'm going to call this for iteration. So like, because we're adding just 3 new tokens at the end of the list, we already know what the values of those are going to be. It's going to be 256, 257, and 258. So we can say for iteration in range 256 to 259. Now you might be wondering why am I including 259 if we just need 256, 257, and 258? This is just how Python works. Is if you do it like this, what it's going to do is it's going to start at this index position and end, but not include this one here. So we are not actually going to be touching 259. It's just going to go up to 258, and then once it sees 259, it's going to cut out. All right. So again, a lot of this is going to be the same. So we want to get our byte pair frequencies. So we want to see, how much is showing up when. So get byte pair frequencies. So we're going to set the token IDs equal to the token IDs. All right, then we are going to set them. We're going to find out what's going on with the most frequent pair. Most frequent pair is going to be the maximum value of this byte pair frequency dictionary that we just derived in the line above. So BP freaks equal, and then our key here is going to be bp freaks.get. All right, and then we want to set up a like a new set of token IDs here. Now I called this first merge just to keep things simple, but since we're going to be looping over this over and over, what we're going to actually do is we're going to overwrite this token IDs back in place. And so we're not going to call it first merge down here. We're going to call it, again, token IDs. So token IDs equals merge token ID, merge token ID. All right, and so we got token IDs equals token IDs replacement pair equals the most frequent pair that we just derived, and then we are going to set our new merge token ID, which is going to be whatever number this iteration's at. So I'm going to call this iteration. So in the first one, it's going to be 256. The second one's going to be 257, and then the third one is going to be 258. All right, and then we just need to add the merge order back in. So merge order for the most frequent pair is going to equal the iteration that we're on, and then our vocab is going to be this iteration value. So this is going to be, again, for the first pass, 256. So basically at the 256th position on our vocab, it's going to equal, again, because we're using the special like Wikipedia example, we need to use our special little lookup table, and then we're going to pass in this iteration. And then now I'm just gonna copy and paste this little bit down here because I'm copying some print statements. These are not important. This is just for illustrative purposes. But basically, when we run this cell here, this is basically the full byte pair encoding algorithm for tokenization. So that so there's a little bit more to it, and we'll talk about that here in a second. But let's go ahead and run the cell just to show you what we got going on. All right, so this is the final list of token IDs after we've merged everything. So we've got 258, 100, 258, 97, 99. And just as a reminder, what our expected final output is going to be these 5 characters. Now we do need to decode them, so we're going to talk about decoding here in a minute, but you can see here that we're already starting to compress the length of the original sample text appropriately. So the original sample text is how long? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters, and we've effectively compressed them down into 5 characters, and we have not lost any information, which is pretty cool too, because we can, again, go back if we wanted to encode these, which we will definitely show. We can do that with the training code that we've developed here. Okay, and I guess one thing I do want to be careful about here is I'm calling this training, and most other people call it training. It's just that training is kind of a weird concept here, because most people, when they think about training a model, it's training this thing that we're gonna, like, we use the model later on for inference purposes. And when I mean inference, that means like it is non-deterministic, like it's like that black box thing, if you will, where we're getting the most probabilistic value, but it's not exactly a guarantee. But in this case, it actually is deterministic. But it's deterministic based off of 2 things. It's deterministic based off of, number 1, are we using the exact same input text? And then number 2, are we running the same number of iterations each time to produce new vocabulary? And what I mean by that is, so in this case, we're training this thing here. If I ran this cell 1,000 times, like not changing anything, we're gonna have the same ending output, but we're still calling it training, because if you look at the input text and how many iterations we're running of the byte pair encoding algorithm, you could sort of look at those as parameters for training, if you will. But again, it is deterministic at the end of the day, meaning that we will always get the same output no matter what. So there is no probabilistic inference here. And that's a little bit different than machine learning as we typically understand it. Okay, what is the time here? All right. Actually, we're moving at a pretty steady clip. I think we'll probably wrap up here in the next 15-20 minutes or so. All right, so let's go back to reviewing this output here. So our final list so that is the 5 values here. So this is our final merge order list. So like I said, we had 3 different merges. We had 97, 97, so that represented the letters A. And then, okay, so this is actually something that, okay, so I'm not crazy. So you might be, I don't know if the Wikipedia example is wrong or if I just screwed something up. It's probably me. I probably screwed something up in here. But basically, what I discovered is I don't know why the most frequent byte pair is actually not AB. It's Z. Yeah, it's ZA. Yeah, it's ZA. So I don't know how I screwed that up. All right, so if all right, let's go ahead and, yeah, I think I messed up my example. So let's go ahead and go alter this. And that's what I was kind of shrugging earlier. All right, so ZA turns into Y, ZA turns into Y. All right, and so now I'm confused. Like, I don't know what I did wrong here. All right, so maybe, all right, so let's keep looking at this. So Y, so ZA, is it ZA? I mean, that's what the byte pair encode, like our example kind of shows here. Let me think about this for a second, because I think I messed something up here, but I'm not exactly sure what it was. Okay, so okay, I guess basically I just don't know how the Wikipedia example is working. Like, this is still going to work for us at the end of the day. Trust me. Because we'll do an encode and a decode, and we'll show you that we're going to get back consistent results here. But basically, what happened here, like, all right, so let me actually go back up to the top here and see what's going on. All right, so we merge these in. All right, so we replace ZA with Y. All right, so then we have YBD, YBAC. All right, so then, all right, so let's take this as the input. All right, so the most frequent pair here is actually going to be YB, right? Yeah, it's actually going to be YB. And then we're going to merge that into X. And then we still get the same. Okay, we still do get the same result. I was just being silly. Okay, my apologies. I need to, before I forget, you know what? Let me go ahead and update my original notebook with this, because I don't want this crap lingering out here. So, okay, that was just me being silly. But yeah, I guess that doesn't really highlight the example. Well, never mind, whatever. But we are still getting the same result at the end of the day. Like, after the 3 iterations, we are still getting the same output. All right, so let's come back into our working notebook here. Scroll all the way back down. All right, so like I said, so first merge order 9797. Then we take our next merge, which is using this newly minted token ID of 256 and 97 to create another newly minted token. And then in our third pass, we are using the newly minted token from the second iteration in the third pass to produce our final third merge. And then so, like, coming back down to our vocabulary, just looking at the last few entries. So these two came from our original instantiation of the byte values, but now you can see we got 3 new entries here. We got value 256, value 257, and 258, represented respectively as ZYX here. All right, so that is the trained tokenizer, but we're not quite done. Like I said, we need to be able to use this trained tokenizer to both encode something brand new and then decode. Like, let's say we have like this value set here, we need to be able to decode this back out. So we need to create 2 new functions. So let's first work on encoding. So I'm going to call this encode, def encode. All right, so we're going to pass in sample text, input text, and then again, we want to be very cognizant of this merge order here. So we're going to pass in the merge order, and we want to follow suit of whatever this merge order is here appropriately. All right, so first thing that we need to do is with our input text is we need to turn them into the byte encoded token IDs. All right, so that's going to be list value of input text dot encode UTF-8. All right, now okay, now when it comes to encoding, if let's say we just pass in a single letter, like the letter H, then the UTF encoding here is going to cover this, and we don't need to proceed forward. And basically what I'm trying to say here is if you pass, we need to be able to a way to be able to account for if like the input text is really small and we don't need to do any merges at all, or like yeah, so basically, all right, let me just type out the line. So basically, if the length of token IDs is greater than or equal to 2, then we're going to continue to run the code. Otherwise, and I'll just, we're going to return the token IDs at the end of this. So, and again, so let's go ahead and build the code to actually do some of these merges. All right, so what we need to do is we first need to, this is where I was talking about again, is we are going to be reusing this function up here, or I'm sorry, not this function right here, although we will be reusing that. We're going to be reusing this function here because we need to be able to find out in our sample text, how often are these current byte pairs showing up, and then we also need to be able to use our merge order dictionary to find out which ones we need to be able to merge first. All right, so scrolling back on down here, so the token, the byte, we're going to extract out the byte pair frequencies once again. And again, this is going to be the exact same function that we used from above. So we're going to pass in token IDs equals token IDs. Okay. All right, now the next one, so this is where things get a little bit different from what we were doing above. So what we were doing above is we were, when we were doing the training of the tokenizer, is we were trying to find out what is the, what is the one that shows up the most often. In this case, what we want to do instead is we want to find out what is the very first value that we should be considering here for merging. So I'm going to call this next pair. So this is going to be the next pair that we want to merge. And so the way that we do this is we want to get the minimum value of the byte pair frequencies. And then the key of this is going to be this special little lambda function here. So this is going to be lambda pair. And then so basically we're going to take the merge order, and then we're going to get either the pair, or we are going to give a float of an infinity value here. Let me pause for a second to remember why we do this here. Okay, I'm blanking why. Andre probably talks about this. Watch Andre's video. He's going to do a much better job than I am. Although I am giving a little bit of context that he doesn't. Like, he doesn't really talk about why arbitrary tokens don't matter. And to be fair to him, he's got his whole YouTube playlist that I'm sure he talks about that in there and somewhere. But yeah, just, go watch his video after this. It's well worth your time, in my opinion. Okay, so next pair. All right, so now we basically want to keep doing the merges until we can't merge anymore. So if if this next pair here that we find is not in the merge order dictionary, not in merge order, then we want to break this loop and we're done. Now let's say it is. So what we want to do then is we want to get the token ID for what is going to be merged in next. So merge order next pair. So basically what this is saying is, okay, if we do find the next pair here, we want to delve into our merge order dictionary. So like, let's say it's 9797, and we want to pull out this value here that we want to start replacing things with. And then, so as you can imagine, take a guess what we're going to be doing here. We're going to be merging things back in with the same sort of syntax that we've been working with so far, or the same function that we built. Sorry. All right, so merge order token IDs. So token IDs is going to be token IDs. And now I hope it's starting to make sense why we call this replacement pair and not most frequent pair, because in this case it's not the most frequent pair. It's the one that makes the pair that we want to replace, and in this case it's going to be the one that we need to do first per the merge order dictionary that we built during the training process. All right, so replacement pair is going to be the next pair, and then our token ID is going to be the the merge order token. Order token is going to be token ID. Okay. All right. So here, let's clean that up a little bit. All right. So again, let's just walk through this again once again, really quick. All right, so we're taking in some raw text. Doesn't matter what this raw text is. We're encoding it into UTF-8 tokens, and then based off of those UTF-8 tokens and the merge order dictionary that we derived during the training process, we're just going to keep going over and over it and start doing our merges until we can merge no more. And then once we can merge no more, then we just return out the final value. So let's do a little bit of a test here. So like I said, so what we should be getting at the end of the encoding here is this value set here. Now we're just for simplicity's sake, this is not a great idea, but we're gonna just, even though we trained on this text, we're gonna use the same Wikipedia example just to really kind of drive this home. So what I'm gonna do here is I'm gonna save this here. I'm gonna call this ground truth Wikipedia encoding. So this is what we expect to see. And then so we're gonna use our excuse me, let me I thought I had to sneeze again. Apologies. All right, so we're going to generate a new encoding here using our encoding function. So we need to encode. We're going to pass in as the input text equals, we're going to pass in the exact same sample text that we've been working with. And then, so let me just to show you again what that is. So it's this string value here, coming back up in here. Yeah. This bothers me that this Wikipedia article is not necessarily correct. Like, I don't know if it's not correct or if they're considering it a little bit differently, but that's not going to stop bothering me. Okay, so, but at least we get the same results at the end of the day. All right, so we need to pass in our sample text, and then we need to pass in our merge order dictionary. Merge order dictionary. Order equals merge order. All right, so, and again, coming back up here, that we're basically passing in the input text plus this, and what we want to get back out is that. All right, so new encoding. All right, and now I'm just going to paste in some print statements just to do a verification here. So, all right, merge order token. Uh-oh. What did I do wrong here? Merge order, hold on. Token IDs equals merge. All right, well now I'm getting lazy. I'm just gonna copy and paste my working code because I'm not really sure where the bug is in here, but clearly there's a bug in here. So I'm just gonna replace this with code this is the exact same code that we wrote earlier. It's just that it's now annotated with pretty comments and everything. Okay, so let's try this again. All right, so there we go. I don't know what the syntax error was. That was probably something silly. But anyway, so we have a ground truth here. So the ground truth here is this. And then we generated our new encoding is this. And then we just do a simple print statement. Do they match? And so we print out, does this one match this one? And the answer is true. All right, so that's encoding. Now let's do it backwards. So like I said, we want to be able to basically take, the same encoding here that we have, and we want to basically do this reverse sort of thing where we bring it back into the plain text that we originally started with. So let's call this, well, no, I guess we still already have that saved here. All right, so let's go ahead and start building the function for the decoder. All right, so def decode token IDs, and then we want to pass in the vocab this time. Because again, the vocab here is basically going to be a little bit of like a lookup table sort of thing. And so the decode function, as you might imagine, is actually a lot simpler than the encode function. All right, so we're going to extract out the text bytes using our vocabulary here. So basically, we're going to have a bytes string, and we're going to start joining everything in our vocab per the token ID. So vocab IDX for IDX in token IDs. Okay, so if that doesn't make any sense, so basically we're looping. This is just a simple Python like syntax here. So we're looping over all of our token IDs, and for every single token ID here, we're finding out what we're basically using our vocab as like a lookup dictionary here, and then we're just keep adding to this string here to get the text bytes. All right, so that's going to be the Unicode text bytes. But again, what we want to do at the very end of this is we want to get the same. We want to, what am I trying to say? We want to get the plain text out of this. All right, so what we're going to do here is we're going to call this text. And so text bytes.decode UTF-8. Now, before proceeding forward here, this is where, again, you definitely want to watch Andre's video because he's going to talk about this much better. So actually, let me, here, it's going to, okay. Here. Okay, I can't remember what example he used, but basically, there, like the way that UTF bytes kind of work is, like if it wants to see things in a very precise sort of way. So if you like have a very, if you don't match your syntax correctly, this decode thing here is actually going to throw an error. And so there's a simple way around that. And again, I am explaining this very terribly, but this is not specifically relevant to the byte encoding dictionary. It's just that like a little quirk of like UTF-8. The way to handle it is anytime we have an error here, instead of throwing the error, we're just going to replace that token. So like, so if it doesn't know how to decode the token appropriately, what it's going to give back is it'll look like this. It's like a triangle-like icon with like a question mark in the middle of it. Again, it's not really relevant to us because all of our tokens are going to decode appropriately, but this is one of those kind of future-proofing things. Is if I was feeding new sample text and like something wonky happens, then at least we're fine because of this little bit here, so then we'll just return the text. And that is the decode function. And that is really the entire thing. All right, well, let's go ahead and run this stuff here. So our expected output here, let's go ahead and set our expected output. Output is going to be XDXAC. So again, we're just following along with our Wikipedia example here. All right, so what we're gonna do here is we're gonna first encode this sample text. I'm just gonna copy this down. We're gonna encode it. And then we're going to take this encoding here, and we're going to pass it back through our decoder to see if we get the what we're expecting here. So we're going to call this new decoding equals decode. All right, not decode. Got to get that E in there. All right, so we need to pass in our token IDs. Our token IDs are going to be the new encoding. So this is, coming from right up in here. And how are we decoding? Well, we're using our vocabulary. So vocab equals vocab. And again, just to kind of, keep a clear line of sight here. So this is our vocab here. Now it's just the last few rows of our vocab because our vocab's 259 entries long at this point. Again, it's just basically using this as a lookup table, if you will. All right. And then I'm just gonna copy in a few print statements here again because I'm starting a little bit lazy. All right, so do they match our decode? All right, what did I do wrong? Oh no! All right, so I clearly did something wrong here. All right, you know what? Let's go ahead and restart and clear all outputs and run all. Maybe I just ran things out of order. Okay, I probably just ran things out of order. Maybe I didn't run this cell appropriately, but there we go. So when we pass through everything, and that's the one nice thing about the byte pair encoding algorithm. I mean, obviously it's going to depend on the size of your text, but it's very fast to train because it's really just all it's just doing is going through the text, finding the most popular thing, and replacing it, minting a new token, and over and over and over. And so it's big O of n, I think is what you'd say that is. And so it's very computationally efficient. So that's why if you ever get stuck and you're doing things in a notebook, my advice would just be to just restart and run all your cells here because it's a blink of a second. Now, if we were training an LLM, obviously you wouldn't want to do that because that would just be a time like suck or something. Okay. All right. So that's correct. So our expected output was XDXAC. Our decoded output was XDXAC. And do they match? The answer is yes. All right. So that is the very naive byte pair encoding algorithm. Now that is as far as I got in terms of my code here. Now, like I was up against the wire, unfortunately here. Now I do want to, in this notebook over here, I am going to put everything together in a massive class, very similar to, I'm just going to go ahead and show Andre what he did. Andre Karpathy. All right, so he's calling his min BPE because his is really clean and easy to follow along with. He's got a couple of files in here, so he's got like a base thing in here. A lot of this is going to match to what we do. I called my things a little bit different here. So like the get BP frequencies, he calls get stats. He simplifies merge down to just merge, et cetera, et cetera. Okay, and what was my point with that? That was to say is, so obviously now that we've trained our tokenizer, we want to be able to save this out and then load it back in. I haven't written the code to do that, but it's pretty straightforward. In fact, let's just go ahead and look at Andre's code to see how he did it. All right, so I guess it's going to be in here. So the way this saves out is into two different files. So it's going to save out into a .model file, and then it's also going to save out into a .vocab file. Ignore some of the stuff for now. We'll talk about this here in a second, but basically what we're concerned about with saving in the model file is our merges. So again, merge order matters. So when we want to do an encoding, we want to follow the same merges, which is why we want to write this out to disk and then reuse it for later purposes. And then in the vocab file, ending with a .vocab extension, it's basically, well, I'm not really sure what this line is doing, but it's basically we're saving our vocabulary into this file. That way we can use it for later. And then basically reversing to do a load, we're basically just reversing what we did for save. And even Andre notes that here, inverse of save. Now, so let's talk about some of these extra lines and stuff here. And I don't have the code written out all of here, but let's build an intuition of why this is very naive. And the reason it's naive is because it's treating it's all right. So let me just turn this into a markdown cell. All right, so we have our word drop here. Okay, so the problem is let's say we have drop. So like let's say let's call this I drop my kids off at school, or there is a I'm trying to think of a I'm not okay, I'm not going to use these examples. So I'm just going to say, let's say we have drop in the middle of the sentence, and then we have the drop at the end of the sentence, and then so it might be followed by a period. A drop might be followed by an exclamation point. Drop might be followed by a question mark. And the problem with this naive encoding here is that it's basically going to treat all of these as separate tokens. And that's not something that we want to do. Instead, what the preferable behavior would be is to treat these as if like this is a separate token. So that way, like we're separating the punctuation from the rest of the word. So that way we are still encoding this as if it's the same token. And then whenever we go and train the large language model, it's being recognized as if it's the same idea. But in this naive form that we've encoded, it's going to encode these all differently. And that's just no bueno, if you will. So let's go into look a little bit at what OpenAI did specifically for GPT-2. And again, Andre Karpathy talks about this much better than I do. But basically what they do is they use a regex pattern to kind of figure out what they should or should not be merging up front. And so if you're not familiar with regex or regex, or if you like, so that stands for regular expressions, and it's basically a fancy way to extract out, like do a search and find and a bit of text here. So this is the pattern that they're using. And so to be completely honest, or no, that's not the pattern that they're using. Where is the pattern? Okay, no, this is the pattern that they're using. This is equivalent but executes faster. Okay, but we'll just stick with this one because it's a little more straightforward. So the way that regex works is you pass in a pattern of what you want to look for, separated by these pipe delimiter values. So you can see here, this might be a little bit hard to read. So let me pull this out into its own markdown. Well, yeah, let me copy this whole thing, and I'll pull this out into markdown. All right. Oh, that didn't. I don't know if that's even. That's not really even easy to read. Well, let me make it clear with some extra spaces in here. All right, don't include these extra spaces. I'm just doing it just for illustrative purposes. All right, well, let's just keep it in this form. So like I said, after these pipe delimiter values is basically like how we're trying to look for things. So you can see here that apostrophe S, apostrophe T, these are very specific ones that they are pulling out of that they want to recognize as their own token. And you might be wondering, well, what do these represent? I imagine that these represent contractions. So if you have like the word it is, here, let me turn this back into Markdown. So it is its, so we have apostrophe T, so do not is don't. And basically what we want to do here is we want to, like, so it is here, it is going to be the same regardless here. So we want to basically treat these as their own tokens. Now, I'm not going to go through the full list here, but let's go ahead and let's pop this into Perplexity and have it read out what each of these things are doing. So let's go into Perplexity. And Perplexity is what I use for stuff. That was a terrible explanation. I love freaking Perplexity. Look how often I'm using Perplexity. All right, so I'm gonna say, explain to me what this bit of regex is looking for. All right, and then let's paste it in. All right, hopefully it gets the right answer. Okay, so, oh yeah, this is going to be perfect. So you can see here that, so these first couple are going to be looking parts of contractions. So this next part here, this /p of L is going to look for any Unicode letter characters. So these are going to just be straight letters here. Now, the one thing I do want to call, it's not, I don't think that the large language model is really recognizing it here, is there's actually a hidden space here. And so when these tokens actually get when these tokens are regexed like this, they actually manifest as something like the word drop here would be space drop, like as such. So like I was noting up here, whenever we encoded my name, so there, my name is David Hunley. So there's 5 characters my first name, 5 characters my last name, but then you'll recall up here, oh, I'm looking in the wrong notebook. My apologies. That my name, where's my name, has 13 tokens here, and that's because there is this character 32 here that represents the space. Now in this, like I said, in this regex tokenizer, it's actually taking that space and adding it into the body of the token itself. So it's not treating that space, or it's not treating that token as if it's a space anymore. And that's not always the case with every token, but you know, that it's just what it is based off of that regex pattern that we're looking at here. And so this is like in my, well, what am I trying to say here? Okay, so one more spaces. So that is the regex tokenizer. So let's come back in here. So that's what GPT-2 did. Now things have gotten more and more complex over time. So the tokenizer for GPT-4 is actually this CL100K base, and it's adding even more special sorts of tokens and whatnot. So it's adding some special end of text tokens and the prompt tokens. Looks like it's got like a more of a complex sort of regex sort of thing here, and it's very easy to enhance these sorts of things like after that. In fact, let's just go and look at Andre's code because he does such a good job here. All right, so let's look at his regex patternizer here. So he's got the same regex here. Let's look at the train here. So this train code here is going to be very similar to what we just did. Excuse me. It's just now that, all right, so we've got our number of merges that we want to perform. And now whenever we actually look at the text chunks, instead of just doing a naive encoding of the text chunks first, we're going to split them out based off of the regex pattern that we just looked at here. And then we're going to split them out on the UTF-8 tokens here. But after that, like if you start to look at the rest of this code, this is all pretty much the exact same thing that we were doing before. We're getting the stats or the most frequent byte pair frequencies. We're indexing, we're merging, we're adding the merge orders, and we're updating the vocabulary. It's the same sort of idea. So it's, even though I've not finished my code yet to add this in or like represent how you would do this, you could see it's pretty straightforward. So it's not like it's like crazily different. Okay. All right, let me review my notes here for a second because we're coming to the end now. And yeah. Okay. Any questions or anything while I am trying to... Okay, looks like somebody had a question, but maybe retracted it. All right. Give me a second to just review my notes because I think we're just going to wrap up here. I'm trying to see if there's anything else that we want to cover. Yeah. Oh, yeah. So let's talk, like, maybe, because I do maybe want to do a follow-up stream here. So, like, right now we're talking about byte pair encoding. Byte pair encoding is not the only method for which we would maybe choose to tokenize things. And Andre talks about this more in his video. Specifically, he talks about sentence piece. And at a high level, what sentence piece is so the sentence piece is the tokenizer that like the llama models use, or the Mistral or Mixtral models use, actually. And it's a sentence piece is an encoding that was developed, I think, by Google. And it's very similar to the byte pair encoding algorithm, except it's not working on the bare byte. It's not working on bytes, excuse me. It's working on the code point level. So it's actually using the individual characters of the UTF-8 instead of like the byte pairs. And like there's a bunch of like I don't know what you want to call it, like parameters that you can tune in sentence piece that like kind of massage the data in different ways. So Andre's opinion on that, and if he ever watches this, which I doubt he will, I apologize if I misrepresent your opinion, Mr. Karpathy, is his opinion on that is like you don't want to go fudging around with the data too much. And that's the case not just with text but with anything, is when you start massaging the data too much, now you're starting to generalize on things that are artificial, if you will. But I don't really have a firm opinion or a thought on this. And I need to go back and review this because obviously, the llama models, the Mistral models, they're doing something right. I don't want to say that they're doing something wrong. So maybe we'll come back in another stream and we'll do that. Maybe we'll come back in another stream and we'll actually build out the Regex tokenizer. Thank you. This is something that I did not talk about at all, and that is, what is the ideal length of a vocab here? And the answer is there's not really an ideal length. And there's not really a specific way to measure how many iterations do we want to run of this byte pair encoding algorithm. So the GPT-4 byte pair encoding algorithm has roughly 100,000 merges. But again, even though we know how many is in the vocabulary, OpenAI has not exposed how, like, the text that was trained on. And then I guess that's another point that we want to bring up is whenever it comes to training the tokenizer versus training the large language model, you don't necessarily want to train those on the exact same data sets. And so and it's sort of like in the idea of general machine learning of where, like, it's what do you call it, data leakage, where you don't want, because you want to be able to generalize on things better, but that's not a hard rule per se. You still probably can get away with using the same text for tokenization versus the actual training. Now, people have found online... Okay, so I am going to pull up this blog post. This is something that Andre brought up. I just think it's really fascinating. All right, so I'm going to do solid gold Magikarp. All right. So there's this great blog post out there that Andre talks about in his video as well. And that is, when you start to do this training on different data sets, is you can start to get some weird results. And so the reason that this post is called Solid Gold Magikarp is because like in the decoding for like the GPT-3 model, like it, and again, Andre explains this much better in his video. He actually gives some working examples. It's like this solid gold Magikarp shows up really weirdly in the vocab of like the final tokenization, but it doesn't. Whenever it was trained on GPT-3, it's like this thing was never seen. And so like what people think is what happened here is that like in the tokenization process, that it seems like OpenAI might have trained on Reddit data because there is a Reddit user named Solid Gold Magikarp. But in the actual training of the large language model itself, that data was omitted, but the tokens still persist. So then, because the tokens still persist and we're still calculating the relationships between words, then you can start to get really weird results. By the way, so I mentioned, the UTF-8 decoding, where it was like that hexagon thing where you have like this, like if something goes wrong with the UTF-8 decoding, this is like what this is what the character looks like, this weird question mark thing. But you can see, where is it at? All right, so what does the string solid gold Magikarp refer to? You could start to see, because it was in the tokenizer, but it was not in the final training, that we start to get some really weird results. And this whole blog post is really fascinating. Andre's talk about it in his videos, really fascinating. Definitely check that out. And yeah, so I see the question in the chat about token limits. I don't know if I answered that question or not. If you wouldn't mind rephrasing that, I'm not really sure exactly what you're referring to there. But yeah, so like tokenization is a really important thing to consider, because you can get some really funky results if you're not tokenizing appropriately. And let me see. So, and Andre talked about this in one of his videos too. So let me see if I can find what he was talking about. Or I know, if I can't find it in here, I know that Jan LeCun recently tweeted about it. Is there like a notebook in here? No, he was working out of a notebook. Okay, well, all right. Let me go find Jan LeCun. Jan LeCun. All right, Jan. All right, we're gonna just look at your media, because I know you talked about this. This is probably gonna be harder to find than I thought. Can I just do a search on Jan LeCun? Jan LeCun Karpathy. All right, and hopefully it'll surface the tweet that I'm looking for. Or maybe not. No, I want tweets, not people. All right, well, I can't find it now. But basically, like let's try a little bit. All right, let me just scroll throughout here. Oh, here it is. This is the precise tweet I was looking for, because this is something that Andre talks about in his video. And he does a much better job of talking about this. But basically, all these different issues here. Why can't LLMs spell words? Tokenization. Why can't LLMs do super simple string processing? Tokenization. All these different things here, and he talks about this solid gold Magikarp here. And again, Andre does a much better job of talking about these sorts of things. And we're coming up on time anyway. We've been running, oh my gosh, well over an hour and a half. Go and check out his video. But basically, the thing I wanted to highlight here is that tokenization is very important. The way we tokenize things is very important to consider. So expect that there will be breakthroughs in tokenization before. And so one of the things that Andre talks about in this video is this thing called GIST tokens. And I can't remember exactly what GIST tokens are, but basically expect that right now the state of the art right now is this byte pair encoding or the sentence piece encoding, but that state of the art could shift. And it could be because of all these different reasons here. And even in my original example, what example? All right, never mind. I don't remember what I was talking about. But basically, I guess this whole stream has all been about just go watch Karpathy stream. Again, I still think it was an extremely useful exercise for me to go through and talk through over this stream. And like I said, I talked about some things about like why the arbitrariness of the tokens does not really matter, and Karpathy doesn't really talk about that in his video. But I guess, you know, I would say you don't need to watch my video, but if you're here, you've already watched it. So yeah. All right. So another question. So if the model has a token limit of 512 and the input text has 600 token, the model may cut off the input or skip parts of it. So I guess let me reread this question again out loud. If the model has a token limit of 512 and the input text has 600 tokens, the model may cut off the input or skip some parts of it, or leading to incomplete or inaccurate outcomes. Let me try to digest that for a second. Oh, okay. So, okay. Now I think I understand the question. So, in this context, we're talking about the input length into the large language model itself. That is irrelevant to what we're talking about here. What we're talking about here, like you could have, there is no limits to how much you can tokenize. You can tokenize a dictionary, but what you're talking about here is if the model only accepts 512. Then the model only accepts 512. Like that's really aside from this point. So that's a good question though. So that's a separate topic for when we train the. So goes back to this whole idea of context length. So like many large language models only have like a context length of like 512 or 1024 or something like that. Or like if you're Anthropic's Claude, it's 100K. What we're talking about here with the tokenization, just getting into like these raw tokens. It can be as many as you want. That does not matter. So I hope that makes sense. Good question, though. All right. So let's go ahead and call it there. I've not eaten dinner yet. Oh, my gosh. It's going to be a late dinner for me. Well, maybe I won't eat dinner. I don't know. So I hope you all enjoyed this live stream. I don't know what the next one we're going to do is. I don't know if we're going to continue on our road to LLM or if we're going to jump back to the LLM evaluation stuff. There is another one. I've got shiny object syndrome right now. There's so many cool things going on right now that I want to explore. So actually one of the next ones I want to explore, maybe this will be the next stream, is a Python client called MLX. So this Python client is one that was created by Apple directly, and it was created with the idea of, we got, Apple's recently in the last couple of years, they've started making their own Apple Silicon chips. So like their own processors, and they're extremely efficient, they're extremely powerful, very fast. And so the idea with MLX is, can we use the underlying GPU power of the MacBook specifically for things like fine tuning or just running a model in general? And so many of you, maybe if you have a MacBook like myself, maybe you've played with something like Ollama, which kind of seeks to emulate that same sort of thing. But MLX is like the direct Apple endorsed version of this. Just came out in like December. I have not had a chance to look at that yet, but I think the implications of that are really, really cool, especially when I think about many developers that work in an organization use MacBooks, and GPUs are very hard to come by right now. So if we can't get a GPU up in the cloud, or if it costs too much money to use a GPU, and we want to do some fine tunings, we already got the MacBook here. Can we use it somehow? So maybe that's going to be what the next live stream is. I think it's a really exciting premise. Again, shiny object syndrome. I keep seeing things. I keep wanting to do them. I've learned so much in the last month, maybe. It's an exciting time to be working in space. So, all right, let's call it here. Thank you again for watching. I really appreciate your time, and we will see you in the next one. Have a good evening.